So this is likely to be the last of the videos that I make of my coding endeavors, namely because it's the last project that I had to do significant coding for. But this was the second project for a Systems and Vibrations class in the fall semester of 2013, as you can see from all of this information up here. Basically what it is it's a turret lathe that has a constant input speed, and then it goes through this fluidic system and ultimately comes out as the spindle speed that is operating on whatever the load is. Now it has the three variables of pressure through the capacitor, flow through the inerter, and then ultimately the spindle speed, and the system responds to a change in this lever angle because a change in the angle results in a change of the transducer property, which affects, the pressure through the entire fluidic system, which has a response that is felt later through the inerter and ultimately through the spindle speed. Now I did two codes for this because this section where we were given values for the various variables and things that we had to find or otherwise calculate had to be scaled for each student so that nobody could replicate their results. So the first code that I did, I pre-scaled all of the values and just input them straight into the code. The second version I did, I actually just used the variables or the values that we were given, and I scaled them according to a scale that could be input to the user, or by the user rather. Aside from that, the codes function more or less the same way. This one actually calculates the value of these variables. This one I just did the calculations by hand. I probably have 6 to 8 pages of hand calculations for this project because that's ultimately how we had to initially do most of these steps, such as finding the Jacobians of the inputs and outputs, getting a state representation. That's actually what this A matrix is. Anybody familiar with state space representation? So this is the Jacobian of the states. This is the Jacobian of the inputs rather. And so it was a 3x3 where the states are, again, pressure through the capacitor, flow through the inerter, and then the spindle speed. The inputs are actually the lever angle, the load being applied to this lathe system, and actually the input omega value. And here are just some of the pages of, I have pages and pages of how I tried to approach this project initially. That's all just rough scratch work. But ultimately you get to these Jacobians of the states and the inputs. I'll actually find, so those are what these equations are, and then again, with how Jacobians and state space work, you derive each of the three equations with respect to the various state variables and the various input variables, and that's what gives you your A and B matrix, or matrices rather. So as these codes run, we get not only the responses of the system, and actually both codes will give me normally similar responses. Right now I have the scaling of this secondary a bit different. What's interesting is that if you change the scale and as it breaches unity, the actual responses of the flow and the spindle speed switch from overdamped to underdamped. And the further you get above unity, the more kind of flagrant that underdamped becomes, or that degree of underdamped response becomes. As you can see, that response will oscillate for a very long while. But again, if we go back to 0.72, it's a very overdamped system. And I just think it's very interesting, just because I'm always intrigued to see behaviors like that of systems like these. And at the time, it was the most difficult state-space system I had done. Since doing this code and since getting more solid in my knowledge of state space, I've tackled larger systems, 4x4s, 5x5s. I've done a 7-state system, but the states were mostly linear as far as the system was constructed in a way that each state would only affect one or maybe two other states. So it wasn't that at any given time I had a 7x7 A matrix where each row of the matrix had non-zero values. It was very much a primarily zero matrix that just had some non-zero quantities in it. So those actually were not very difficult, but at the time this one was. I'm going to apologize in advance for any skip that you might have just experienced while watching this. I'm still pretty new to the video capture program that I'm using. In short, I have never used it until tonight to record the videos of these codes. So yeah, but the gist of the program and of this script, and there's that output response again. But so it's coded to where you can see there are 3 transfer functions. What these transfer functions represent is the lever input to each of the outputs, where you can see this C matrix is found within a for loop, to where it's identifying either the pressure through the capacitor, the flow through the inerter, or the spindle speed as the output that is under consideration. And then it finds the step response and the system response of that transfer function, or the transfer function that comes about once you process the state space of it. And so again, between the two codes, most of the functionality is interchangeable. They both have subplots that group up the outputs. They both have a basic, roughly the same state space representation, honestly. If you were to, or I guess if I were to, since I have control over the computer, if I were to space these out and format it to have the same appearance as the A matrix in this one, you can see that they're roughly the same. Actually, not even roughly, they're identical. And so it allows for 2 similar yet slightly different approaches to manipulating the information and portraying it through MATLAB, and producing outputs that people can read and interpret and understand and kind of see how these systems would respond. But this was probably one of my favorite projects that I had done throughout my time at Texas Tech, just because it was so ridiculously challenging at first, but ultimately rewarding, because anytime you have a difficult project but you have sufficient time to work on it, and a professor who will help you get the basics and kind of give you the tools that you need to really develop to be able to wrap your head around these kinds of things, the side effect is that you grow more as a scientist and as an engineer. And so, whereas when we first got this project, it would take me days to get even one of the system equations completed. Now I can do state space, but almost in my sleep, I guess I would say, especially for a 3-state, 3-input system like this. I haven't come across any that are the really difficult kind of high-order real-world systems that, you might have a 12x12 state matrix or some even higher order system than that. But from what I've seen, as far as the kinds of systems that most college students have to deal with, this is probably one of the more difficult ones that I've, seen in years. So it was just rewarding overall. I think, and I had a lot of fun with it by the end of it. Mostly because all of my peers were still struggling with the project by the time I was really getting it refined and coded and formulated where I wanted it to be. So I got to play tutor with that, which is always interesting. Anyways, I might upload another video of some code that may lay in my future if it's cool and demanding enough, but it's a coin toss ultimately. But for anybody who's taken the time to watch all of these videos, I thank you.